Okay, so I've recopied this graph here so we can dissect it in terms of area. So now I have this sort of trapezoid-shaped thing. What I'd like to do is to split it into a rectangle and a triangle. And so we're going to call this area down here area 1, and I'm going to call this area, this triangular area up here, area 2. And we're going to just use our kinematic variables to calculate the areas of these two things. So let's start with area 1. So area 1 is going to be equal to, well, I have the change in time here on the bottom, and I have the initial velocity. So this is just equal to the initial velocity times the change in time. The initial velocity is the vertical axis, and the change in time here is the horizontal axis. Okay, so that was relatively straightforward. Area 2 is a little more tricky. Area 2 is equal to, so this is a triangle, so the area is 1/2 times the base of the triangle, which is delta t, times the height. And so now the height is Vx final minus Vx initial. So that's my height. OK, and so, well, that actually wasn't so bad. So now we can go and see what we've got here. So in order to write down equations from this, what I'd like to do is assume, in both cases, that t initial is equal to 0, so that delta t is equal to t. So if we do that for the first case down here at the bottom, then this area 1 is going to be equal to Vx initial times time. And if I go up here, we need to look back at our definition of acceleration. So the average acceleration is the change in velocity divided by the change in time. So this quantity here in the parentheses is actually the average acceleration times the change in time, because delta v is equal to the acceleration times the change in time. So in both cases, the change in time is just t. So I have a factor of t here from this part of the equation, and I have another t here. So this is equal to 1/2 times the acceleration times time squared. So we said that in order to find the total distance that I travel, I have to figure out the area under the velocity versus time curve. Now we've just done that. So we can write that the displacement, which is x final minus x initial, is going to be equal to area 1 plus area 2. And so if I take these pieces of the equation down, this gives me Vx initial times time plus 1/2 times the x acceleration times time squared. And so in order to get the final kinematic equation, what we're interested in is the final position as a function of time. And so let me redefine this x final as just x. And if I do that, and if I add x initial to both sides, I can get our final version of this kinematic equation, which is that the position as a function of time is going to be equal to the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. And so this is the second of our important kinematic equations.